Hi, and welcome to the Physics 3 Tutor. And before we get started with any of our actual topics, I just want to say that Physics 3, which covers electricity and magnetism, is actually my favorite part of physics. So hopefully some of my enthusiasm for this part of physics will come through in the lectures and in the examples as well. And I can remember back to when I was a young boy and like many kids playing with magnets and holding one magnet up and another one next to it and just being incredibly amazed. I could play with hours with these things because, putting a magnet up against another one and just feeling that it can push away from the other magnet, or if you flip it over and it attracts that magnet and slams them together, and putting a piece of paper between them, and the fact that they still attract and repel through paper and wood and plastic. I was just fascinated with that, and even today, with my own children, I do those things and play with those easy little toys that'll occupy them for a period of time. And the reason is because really we take things like that for granted. We all have magnets on the refrigerator, right? We all have magnets in all over the house and other things like that. But when you really think about it, a magnet is really almost magical. Somehow this little piece of whatever it is, metal usually, some kind of metal, is somehow able to attract other magnets and repel other magnets, and also metal, and it's doing that without any sort of visible string or anything connecting them together. I mean, somehow this force is acting through thin air, much like gravity acts through thin air. In fact, we know we don't need air for either of those things. Gravity and electricity and magnetism, they occur through empty space with nothing at all between them. You can suck every single atom out of a jar, every one of them, and you stick a couple of magnets in there and they'll still attract and they'll still repel. And it's basically this force is being transmitted through nothing, through empty space. So we, over the centuries, have learned a great deal about why this happens, but as you get deeper and deeper in physics, you'll realize that all of the answers aren't really there. We don't know all of the answers, and that's why I still find it fascinating. Because even as I got down into advanced physics, and even as I got into quantum mechanics, there are still things about magnetism that no one understands, the exact reasons and mechanisms behind why it happens, but it does, right? The other thing I was fascinated with is, when you're kids, you have walkie-talkies, right? So one person has a walkie-talkie and you go around the corner with another walkie-talkie. And I was just fascinated that you could press a button on this box, this little thing you're holding in your hand, and talk into it, and somehow my voice is being changed into something that's then sent over, again, empty space, thin air, into basically nothingness. And then 100 feet away, someone with another box can receive that and listen to exactly what I've said. And on top of that, there's almost no delay. We know now that it's the speed of light traveling between here and there, the radio waves, but back then I didn't really understand that. It was basically instantaneous. How can that be? Those are just two examples of things that fascinated me from a very early age, and I hope that you don't overlook those things in your everyday life. It really is amazing that we can transmit information through empty space for millions of miles and use it, do it using an electromagnetic wave, which is a radio wave or a microwave or something like this. It's very fascinating. So we are going to embark on our journey to try to understand the ideas of electricity and magnetism. And along the way, we're going to start talking about electric circuits. We're going to talk about what circuits are. We're going to talk about the more fundamental things about the electric field and the magnetic field and how they interact. And finally, at the very end of this course, we'll talk a lot about electromagnetic waves, which you're bathed in every day of your life, and how we're able to transmit energy and information in an electromagnetic wave. And I hope that this course will give you the tools that you'll continue to keep an interest in it and go on and learn even more and more about it. Because believe me, even if you finish this course, you will not understand everything about this stuff. It's just too deep. People spend their entire careers studying this stuff. So you have to start somewhere. And in my quest to make sure that I don't assume you know anything at all, we're going to start at the absolute beginning. We're going to start this section, which is titled Electric Charge and Coulomb's Law. So like you might think, we're going to start off talking about what exactly an electric charge is, and then as the sections go on, we will build upon that and start talking about electric fields and all that stuff. So first, let's start out with the basics, things that I think you'll all basically know. Everything around you is made up of atoms. right? Now, I've never seen an atom. Well, they're getting pretty close to being able to show little images, so to speak, of atoms, but I've certainly never seen one with my own eyes. But all of the experiments over the hundreds of years in the scientific age have shown that everything around us is made up of atoms. And inside those atoms, in the nucleus of the atom, in the center, you have the protons, right? This is back from your basic physics and your chemistry. You have your protons. Those have positive charge. That's why we call them protons, positive, right? And inside that nucleus, you also have these things called neutrons, which don't have any charge at all, but they do have mass. And then, so those are in the very tightly bound nucleus, in the very center of every atom in your body and everything around you. Now, outside of that nucleus, you all know that we have electrons, which are these, again, charged particles. And these guys don't have a positive charge, they have a negative charge. So that's sort of the duality. You have the positive charge in the nucleus and you have the negative charge in the electron. Typically, when you start talking about atoms and you're really little, you're taught that atoms have the electrons that go orbiting around the nucleus, just like the sun and the planets that orbit around the sun. That's pretty good for a basic understanding, but in real life, an atom is not really constructed that way. When you go into quantum theory, you'll realize and understand that the electrons really aren't these little nuggets of matter that you might think about, beach balls, and they don't really orbit in a nice, beautiful orbit like Mars might orbit the sun. It's really a cloud, and there's a probability that you'll find an electron at any given place at any given time. And no one's ever seen an electron either, so we're kind of using our scientific imagination to ascribe what it might look like or what it might be. But in the typical textbook drawing, you have these little beach balls in the nucleus. They're called protons and neutrons. Protons have the positive charge, and you have the electrons going around, and those have the negative charge. So that's what we have in our basic understanding from when you were a little kid, right? I think everybody watching this video pretty much knows that. Now, other thing you probably know, and if you don't, you'll definitely have to know it, and you will know it by the end of this section, is that opposite charges attract and like charges repel. And I think 99.9% of everybody watching this knows this, but I'm not going to assume that you do, so this is something you have to understand. Opposite charges, they attract each other. Okay, they attract each other. We'll do it like this. Same charges, they repel each other. Right? So what does this mean? Opposite charges attract each other. What this means is that if I have a proton sitting right here, and I have an electron sitting right here, I haven't even really told you all this yet, but a proton has a positive charge, and I'll tell you exactly what the value of that charge is here in a little bit, but it has a positive charge, right? And this electron has a negative charge. It turns out that the proton and the electron have exactly the same charge. It's just that one's positive, one's negative, right? Those two things, if I were to stick a proton right here, and if I were to stick an electron right here and just let them go, over time they would come together and smack into each other because those opposite charges, meaning opposite signs of those charges, are going to set up a force that's going to cause them to attract. Now, why does that force exist? Why does that force exist? I cannot tell you that. This course will not tell you that. And probably, I don't even think humanity knows that. That's a fundamental thing of nature. Why does gravity occur? Why does opposite charges attract? Those are things that we're still striving to understand ourselves. So don't get too wrapped up into that. That's an observation. You can take a positive charge and you can take a negative charge and you can stick them in a jar and suck out all the air and see how they move and they come together. And that's why we say opposite charges attract each other. All right? Now, what I'm writing here is that if you have two charges with the same sign, right? So two positive charges or two negative charges, those guys will always repel each other. If you have the same type of charge, the same sign, those guys will always repel each other. So if I have a vacuum jar here and I stick an electron here and I stick another electron right there and I watch what happens, they're going to move apart from one another. And if I stick a proton here and a proton here, they're going to move apart, right? So that's very, very important because as we start calculating the force that comes about because of this attraction and repulsion, you're going to have to remember that like charges repel and opposite charges attract because that's going to help you understand what's happening in your problem. So that's something you'll have to commit to memory. The good news is I think most of you already knew that anyway. All right, but we're going to use that result and that fact in every one of the problems that we work in this course, almost every one of them. Okay, and also, so you have, protons and you have electrons, but from your chemistry days, you might remember that an atom, which may have, 50 protons in the nucleus and 50 electrons orbiting around, so to speak, that you can create maybe an ion by taking some of those electrons away, or maybe you can add some extra electrons into the atom. In other words, you can give that atom a net charge usually by taking electrons away from the shells, on the outside of the atom there. So in that case, you have an atom that has a net charge because you see the positive charge in the nucleus and the negative charges in the electron, they cancel each other out because they're opposite of one another. And so in general, all atoms, like in your body, they have a net zero charge. In other words, you pick up a grain of salt or you pick up a morsel of dirt, doesn't have any positive charge or negative charge to it on the whole, even though inside is billions of electrons and protons, because you have so many of opposite sides that they all cancel each other out. But you in the lab can take a chemical and you can take some electrons away, leaving the majority behind, and you can create a net positive charge or a net negative charge. Like maybe you might have something like this, like these are some protons here in the nucleus, some neutrons also, and then orbiting around you might have these 4 electrons. Well, here you have, and these guys, just using the cartoon that we have in basic understanding of physics, these things are orbiting around. I told you that's not really how things work as far as we know, but it's a good image for you to keep in your head. So this atom is stable. It has the same number of electrons as it does protons, so it's a net zero charge. There's no net charge because you have the same number. But if I take one of these electrons away, I literally might take one away, and I have 3 of them left, then I'll be more positive charges in the middle than there will be negative, and so this ion would have a positive charge, a net positive charge. And also, if I wanted to add another electron here, then I would have a net negative charge for the whole atom. So what I'm trying to say is that this ion may have a net negative charge, right? And if I stick it next to another identical ion with a net negative charge, these two guys would repel because this would be the same charge as this, right? So this like charges repel and opposite charges attract applies to electrons, protons, or anything that happens to be charged. Even if it's, if I could take a bucket, a metal bucket, and add extra electrons to it and make it negative, then that thing would obey what I'm telling you here, that opposite. If I had another bucket with the same sort of thing going on, then those two buckets would repel each other, so to speak. So very important. That's why I'm kind of beating it down in your head. And one practical example of that would be everyone on a cold winter day has shuffled their feet along the carpet, right? I know I used to love doing this. Shuffle the feet along the carpet and then go touch a doorknob. Or better yet, go touch your mom or dad. Get a nice zap, right? Electric zap. And you can even see the zap a lot of times, especially if you turn the lights out. You'll actually be able to see the little spark right there. What's happening there is that as I'm shuffling across the floor, the shoes are touching the floor and my body is picking up extra electrons from the floor. If the humidity is low and it's dry air, then those electrons are able to come up into my body, and my actual body, much like the atom right here, has picked up extra electrons. My whole body has picked up a few billion extra electrons just from shuffling across the floor. So when I walk over to mom and dad, or if I walk over to a doorknob and touch it, then I'm putting my finger in contact or very close to something that has less electrons than I do. Then these electrons in my finger, they want to jump off and go off to another body because I'm full of them and I have too many of them, and they're wanting to go to something else that has fewer of them. And so that little piece of light that you see right there is literally, it's basically the electricity flowing from me to whatever it is. So that's a practical example of electricity that you've seen in your everyday life, and it all comes about because of shuffling across the ground. And you've seen it with balloons too. You can move a balloon along your hair, and then your hair kind of pulls out to it like that. It's because of the electrons being shuffled back and forth between the two objects, causing a force to occur. In that case, the force is pulling your hair away from your head. All right, so now we haven't done any math yet. This is just sort of a basic idea of what is charge. Charge is something you can't see. Charge is something you observe. A long time ago, they realized that if you put two things together, they attracted. We called one of them positive, one of them negative. And if you take two of the like things and you put them together, they're going to both repel. So we called those both positive or both negative. And so that's how it sort of evolved. So the details of charge goes like this. The SI unit of charge, the SI unit of charge is called, very important that you know this, and you will, the Coulomb. The Coulomb. And the unit for that is just the letter C, right? It's a Coulomb. To give you an idea of what that is, none of these things really make total sense until you sort of see how you relate it. One electron is equal to negative, because electrons are negative, remember? 1.60 times 10 to the negative 19 coulombs, right? So you can see that a coulomb is a very large unit, because one electron, one little tiny morsel of something that we call an electron in every single atom in the universe is negative 1.6 times 10 to the minus 19 coulombs. That means a coulomb itself is a very large number. Electrons, which are tiny, tiny, very small fraction of that. And so if you remember, I told you protons has exactly the same charge as an electron, but it's positive. So a proton charge is 1.6 times 10 to the negative 19 coulombs. Only difference between the two is one of them's positive and one of them's negative. You put these two guys in the room together, they're going to begin to come together and attract, and if you have two electrons next to each other, they will repel. If you put two protons together, they will repel. Now what we're basically leading up to here is a equation that tells you what the force is between these charged objects, and that's basically what we're going to do right now. All right? What we're going to talk about now is Coulomb's law, which is probably one of the most important things in all of physics, and certainly in this course. Coulomb's law. And basically, Coulomb's law, in your head, just try to commit this part to memory at least. Coulomb's law tells you what the force is between two charged objects. Just like gravitational force we talked about in physics 1, some constant g, mass 1 times mass 2 divided by r squared. That was the gravitational force. That's something you measure, out in real life. You can measure the gravitational force, so they come up with that gravitational equation from Newton's laws that thing comes from. That's what we use in all of physics 1. Well, in physics 3, for electricity and magnetism, Coulomb's law is just as fundamental. It describes the force between two charged objects due to the electrostatic force between them. So here's what it is. The force between two electrically charged objects is the following thing. And it's really not a very complicated equation, but let me write it down and we'll explain it. The force between these two objects is equal to 1 over 4 pi epsilon naught, we'll talk about that in a second, charge number 1 times charge number 2 divided by r squared. R is the distance between them. So let me just make sure everybody knows this is Coulomb's law. This is not something you derive. This is not something that you figure out. This is something you measure. The force between these things, you measure it 100 million times and you find out that this law actually fits the forces that you measure in the laboratory. All right, so let's look at what this is. What is this? R is the distance between charges. Makes sense, right? You have to know what the distance between them. I mean, you obviously know that the farther apart these charges are, the smaller the force is going to be, electrostatic force is going to be between them, right? Obviously, both charges matter, so you have both charges up here. These, I'm just going to put a little bracket right here. I'm going to say these are the charges. And these charges are going to be measured in coulombs, just like we said right here. An electron is this and a proton is this. If you had 10 electrons on an object, it would be the electron charge times 10 would be Q1, and then you would have whatever you had for Q2 for the other object. So it's the total charge in coulombs times total charge in coulombs for the other object, the distance between them of squared. Now this stuff looks really complicated, but it's really not, because what you're going to find out, let me write this down, 1 over 4 pi epsilon naught is equal to, think about it, 4 is a number, pi is a number, epsilon naught, I haven't told you yet, but it is just a number. It's a constant that you find in nature. So when you do all this division, this entire thing, right, this whole thing right here is 8.99 times 10 to the 9. And the units you won't really need to know that much because you're just going to use this number, but it's Newton meter squared per Coulomb squared. And that all these units come from the units of this constant right here called the permittivity that we'll talk about in just a second. So just remember that when you're using Coulomb's law, this is the sort of the form that you'll see in your book, but just remember all this stuff in front is nothing more than a constant. This is the constant. So really Coulomb's law is this number times the stuff that matters, which is the charge of the objects you have and the distance between them. That's what you have here. All right, now let me write a few more things down here. Where epsilon naught is something we call the permittivity. We'll talk a little bit more about it later, but that's what it is. It's permittivity constant, right? And it's equal to a number 8.85 times 10 to the minus 12. And the units, Coulomb squared, Newton meter squared. These are the units here. And this is the units of this guy right here. All right, lots of stuff to talk about here. Lots of stuff to talk about. Don't get too worried about this. What you have, you know, is that in every branch of physics, there's always going to be some constants that pop up when you start studying it. I mean, in geometry, pi comes up a whole lot because pi is just sort of ingrained in the fabric of where we live and this universe that we live in, right? The ratio of the circumference to the diameter of a circle, basically. That's a very important constant, right? You have other constants out there all throughout physics. You have the gravitational constant, right? The gravitational acceleration. That was very important in Newtonian motion. In thermodynamics, you had specific heats and other things that were really important in that section in physics. Here, a constant that pops up a lot when you're talking about electricity, electric fields and things like that, is called the permittivity, and it just has to do with how electrostatic forces behave. The only reason that you write Coulomb's law this way in terms of 1 over 4 pi E naught instead of just using this number is because this permittivity epsilon naught rears its head as you go down the road. So we're going to introduce Coulomb's law in terms of showing you that, yeah, this constant is wrapped up in there because 2, 3, 4 sections from now, you're going to see the permittivity appear again, and so you won't be all like, where did that come from? Permittivity is a fundamental constant of, you know, of nature, just like the gravitational constant is a fundamental constant of nature. You just haven't seen it before because you haven't studied electricity and magnetism before. So don't be too worried about that. When you're calculating the force between objects, you have two options. You can just use this number I've given you because the book has already pre-calculated what this is out front. Or you can leave it like this and just plug in for the permittivity, which is given here. You're going to get exactly the same answer. Now, one thing I want to point out to you here is that the force between two objects that have charge is dependent only on the charge of the individual objects multiplied together divided by the distance squared between them, right? And we're using coulombs up here and we're using meters down here, just like we do all in physics to keep our units nice. We're using these units here for this constant, and everything out in front is simply a constant. So the only thing that the force really depends on is the distance between the two things and the charges, which is sort of what you might expect. Now let me draw a comparison real quick. Compare. Let me ask you, what is this? What is this? G m1 m2 over r squared. What equation is that? Do you remember? That's back from Physics 1. This is the gravitational equation. This is the equation that tells you if you have two masses, m1, m2, this could be the Earth, this could be you, or this could be a satellite or something. You multiply them together, divide by the distance squared between them, and then again there's a constant out front, and we presented that constant much in the same way I did with this one back in Physics 1 without any proof at all. I just said this is a constant, it's measured. Use it, right? And so this guy tells you, if you put this stuff in, tells you what the gravitational force is. Notice that the electrostatic force from Coulomb's law that comes about as a result of two charges on two different objects has exactly the same form as the gravitational equation. I mean, these equations are exactly the same two equations. This is charge 1, charge 2, mass 1, mass 2, distance squared, constant out in front, constant out in front. That, my friends, is something that you should maybe even pause the video for a second and think about. It's really, really amazing that that actually happens, that two completely different fundamental phenomena, one that we call gravity and the other one that we call electricity, electrostatic force between two objects, both of which you can measure in real life in the laboratory, they're not way out wacky things, have exactly the same form for their equation. That tells you that somehow on a more fundamental level, electricity, or the electric force, and the gravitational force share some symmetry, and they share some characteristics, and they're probably both derivatives of some even more fundamental thing in nature that we don't even understand yet. And that's what lots of scientists are actually trying to figure out, even today, is trying to take the forces in nature, because all of them, or at least a lot of them, seem to behave in a very similar manner. And maybe there's something more fundamental than gravity. Maybe there's something more fundamental than electric charge that we've not even discovered yet. And this symmetry here is a clue that that's true. Now, I don't know what the answer is, I can't tell you that, but I'm trying to motivate you to tell you that this stuff is really, really amazing. And so you can use this equation just like you use the gravitational equation, and you'll be in good shape. So when we do our problems, we'll be doing that. Most of the time, we'll just stick 8.99 times 10 to the 9 right here. We'll put our charges in, we'll put our distance in, we'll get our force. Now, there's one more thing I want to say before we actually go off and work problems, which we'll be doing right now, actually. That is that when you put your charges in here, 99% of the time, different books teach you different ways, but the way I would like you to do it, 99.9% of the time, that means almost every single time you work a problem, I don't want you to put negative charges and positive charges up here. In other words, I want you to put absolute values up there. So if you have a proton, it's got a positive charge, you're just going to put the number in there just like you would think. If you have an electron, or if you have some negative charge, right, I don't want you to really put a negative sign up there into the whatever charge you have here. I want you just to put the value of the charge, the absolute value of the charge. And what we will do is, from our knowledge, and so what you'll do is you'll put the value in here and you'll calculate a force, but the only thing that negative positive is telling you is if it's an attractive pulse or force or a repulsive force. And what we will then do at the end of the problem is think about what the charges are, if they're negative or positive, and we will determine for ourselves if it's repulsive, pushing away from one another, or if it's attractive and they're actually coming towards each other. And that's, different books have it differently. Some books have it written just like this. Some books actually put absolute value bars around these charges here. Because if you put negative values here, you're going to get a negative force sometimes, and then you'll be like, well, what's a negative force? Which direction is that pointing? It's just easier to keep positive numbers up here, and then if you have, depending on if they're both positive or both negative or one of each, at the end you'll know which way the force is pointing, because we've already talked about like charges attract, and like charges repel, and opposite charges attract. So let's go ahead and erase the board. We have several problems. Let's go ahead and do this. This is the only equation in the section that we're talking about, is Coulomb's law, the fact that you have attractive and repulsive forces as a function of electrostatic charge. Let's go ahead and work some problems. Okay, our first problem goes like this. What force exists between two charges of 1 Coulomb separated by, there's two parts to this problem. First part is by 1 meter. And of course, after we do that, we want to see what the force is between those same charges when they're 1 kilometer apart. So this is very much what you call a plug and chug kind of problem. You know what the Coulomb's law is that tells you what the force is between two charged objects, basically due to their charges. So what we're going to do is we're going to plug in the numbers here and see what we get for the answers. So remember that Coulomb's law is the following. The force is equal to, and it was 1 over 4 pi epsilon naught, but we're going to use this constant that I told you is what it reduces to, 8.99 times 10 to the 9, right, times the first charge times the second charge over r squared. Right? And what we know is both charges are 1 Coulomb, and the fact that there's no positive or negative in front of that, it means both of them are positive, just like you might think. If it doesn't say negative, then you assume it's positive, just like in algebra. So, two charges, 1 Coulomb, and they're separated by, first let's do 1 meter. So what we're going to have is 8.99 times 10 to the 9, and over here you're going to have it's 1 Coulomb, and the other charge is 1 Coulomb. They're both positive. We're just going to take the absolute values there. It's just the same thing, 1. And you're dealing in coulombs up here, so you just put the 1. On the bottom, you're dealing in meters, so it's going to be 1 squared, the distance between the two charges. So this is a really simple problem, right? You've got 1, 1, and 1 squared, so the answer, if they're 1 meter apart, is 8.99 times 10 to the 9 newtons, because the answer you're going to get is going to be in newtons. It's a force. Now remember, force is a vector. It's a magnitude, how strong that force is, and it has a direction to it. Every force you've ever dealt with has been a vector. Right now, standing on the ground, the force of gravity is pointing down. It's a vector force pointing in a certain direction. Now this guy is a vector force also. So if you have two charges and they have both the same sign, are they going to repel each other or are they going to attract each other? You have to remember that from the first part. We said that like charges always repel. So this force is repulsive, right? And just really briefly, I mean, this means that if I had my charge here and I had my charge here, and this is 1 Coulomb and 1 Coulomb, and this was 1 meter, then the force would be 8.99 times 10 to the 9 newtons pushing outward. It would be repulsive. They would be trying to move apart from one another, right? That's what that means. Now notice that it's a huge force we calculated for this problem, and that's because 1 Coulomb of charge is a huge charge. I mean, huge charge. We said 1 electron was 1.6 times 10 to the minus 19 coulombs. That's 1 electron. So this is a very huge charge, and that's why the force, if you could ever build something with this much charge in two different objects, it would produce an incredible amount of force between them. Now, doing this is going to be almost impossible to do. I mean, that's just, you know, that's just a huge amount of charge. Now, B is, what is the force if these guys are 1 kilometer apart? So it's the same sort of thing. It's 8.99 times 10 to the 9. Charge 1 and charge 2 stay exactly the same. The only difference is the distance between them is 1 kilometer. But you know, you never want to work with kilometers. You always want to work with meters. So it's 1,000 meters, and it's squared because it's r squared. So you'll have 8.99 times 10 to the 9, and you'll multiply. When you do this division here, 1,000 squared, 1 divided by 1,000 squared is going to be 1 times 10 to the negative 6. And so the force, when you do this multiplication, is going to be 8990 newtons. And again, is it attractive or repulsive? We have changed nothing. We have two charges with the same sign. That means they repel each other, so it's repulsive. Or they repel each other. And notice that the force is a lot less, because even though the charge is the same, I have separated these things by a huge distance, 1 kilometer, 1,000 meters. So the force, even though this is still a pretty big force, is much, much less than the original one, and that's because those guys are much, much farther apart in the second case. So Coulomb's law literally is just like the gravitational formula that you learned way back in Physics 1, so you have a lot of experience with dealing with that already. Second problem says, what is the distance between two charges, Q1, 26 microcoulombs, and Q2, negative 47 microcoulombs, if the electrostatic force between them is 5.7 newtons? So this is a little bit less than a plug-and-chug problem. It's not so simple that you just plug in values and calculate a force, but essentially you're going to be using Coulomb's law for all these problems. So what is Coulomb's law? Same thing again. It's 8.99 times 10 to the 9 times Q1 times Q2 over R squared. And this guy says, what is the distance between two charges? So we're going to be calculating R if the electrostatic force is 5.7 newtons. So the force between them is 5.7 newtons. So let me just go and continue to write this down. 8.99 times 10 to the 9. Now what do I have for Q1 and Q2? Q1 is 26 microcoulombs. So what you have is, that's 26 times 10 to the minus 6, because micro means 10 to the minus 6. 26 times 10 to the minus 6 coulombs, or coulombs. Q2 is negative 47 microcoulombs. Now remember, when I use Coulomb's law, I'm generally not going to put my negative signs in here. It just makes it easier for me to think about. So 47 times 10 to the minus 6 coulombs. And over the bottom, I'm just going to put R squared because that's what I'm trying to calculate, right? Now, we know that one of these charges is positive, and we know that one of these charges is negative. So the charges just tell you that they're going to be attracting each other, and that's actually what it says. The electrostatic force between them is 5.7 newtons. So that just tells you one of these things is positively charged, one of these things is negatively charged, and they're going to attract each other. Putting the negative sign in here doesn't really add any additional information because the magnitude of what you calculate is exactly equal to what's over here. If you stuck a negative in here, you're just going to get confused because you'll have a negative on this side of the equation and you'll have not a negative over here, and you could get into a situation where you end up calculating a negative r, or in this case you'll try to solve for r squared and take the square root of a negative number and get really confused. So that's why I'm telling you that yes, we put negative and positive charges on, signs on the charges to tell us if they're going to attract or repel, but that's really the only reason we do it. When you're using Coulomb's law, it's a lot easier just to put the numbers in there and just think about what the sign is telling you to understand the physics of the problem. Okay? Enough preaching. So let's continue on to this. So if I take the 5.7 and I divide by this, 8.99 times 10 to the 9, I'm going to get 6.3 times 10 to the negative 10 on the left-hand side. On the right, so I'm just divided by this. On the right, I'm just going to multiply these two numbers together. 1.2 times 10 to the minus 9 over r squared. Over r squared. So to solve for r, let's multiply by r. So we get 6.3 times 10 to the negative 10 r squared. Just multiply here. On the right, we're just going to be left with the 1.2 times 10 to the negative 9. So to solve for r squared, we'll just divide both sides by this. So r squared will equal 1.9 when you take this and divide it by this. And so r, when you take the square root of both sides, is going to be 1.4, and you're always dealing in meters, so it's 1.4 meters. So you see what I'm trying to say. If you tried to put a negative sign in here without thinking through exactly what was happening, you might get into a situation where this is negative, so when you solve for r squared, you'd get a negative number, and you try to take the square root, and you know that the square root of a negative number is imaginary, so your calculator is going to return error, and you're not going to know what's going on. There are different ways to do this, so your book might tell you something different, but my advice is just put the numbers in here, don't put the signs in here, don't put any signs on the force over here, and you are just going to have to remember at the end of the day that these charges, since they're opposite, means it's an attractive force. That's really all that that's trying to tell you. And the force was given to you in the problem, 5.7 newtons. So these guys are 1.4 meters apart. Okay, now we're going to get into some problems that are a little bit more challenging and require you to do a little more thinking ahead of time to set them up properly. There won't be as much of the plug and chug variety, so let's get into it. Charges Q1 and Q2 lie on the x-axis at x is equal to negative a and x is equal to a. How must Q1 and Q2 be related for the net electrostatic force on a third charge, positive capital Q, be placed at x is equal to positive a over 2 to be 0? So you see, this is the kind of thing where you have to read a problem 3 times, and then you must draw a picture. And by the way, if you haven't been doing that in all of my courses, I've been saying in physics, you have to draw a picture anytime you can. It's going to help you. Don't try to dive into this and start trying to, this is the kind of thing you would look at it and you would have no idea how to start it. You have to draw a picture and just start writing down equations, and that will lead you down the path to success. So let's read it one more time. Charges Q1 and Q2 lie on a line on the x-axis. So you're going to have an x-axis, you're going to have 2 charges on it. Those charges are at negative x is equal to a and positive x is equal to a. How must they be related to each other? So the net force on a third charge, positive capital Q, so some other charge placed on the axis at a location given at x is equal to a over 2, so that the force on that guy is 0. So again, let's draw our picture. We're going to start out by drawing a line like this. And what we're given is that Q1, so let's say this is 0 right here. This is the x-axis, that's 0. Q1 is here at negative a, x is equal to negative a, and charge Q2 is at positive a over here. So that's given by the first sentence of the problem. How must they be related so that the force on a third charge plus Q placed at positive a over 2, and it's a positive charge plus Q, how how can this force be zero? So you're thinking about this, and what you need to think about is, look, I have a charge here and a charge here, one on either side of another charge here, right? And so there's going to be a force acting on this charge due to Q2. That's going to be given by Coulomb's law. And there's going to be a different force, totally separate, coming from this charge here, acting because of this charge, much like gravitational forces, right? You could have a force because of the moon, you can have a force because of the sun, and the resultant body is going to move based on both of those forces acting together, right? So you have a charge, one force is going to come from this guy from Coulomb's law, another one's going to come from this guy from Coulomb's law. Of course, he's not exactly in the middle, so it's a little unclear how he's going to behave, but what we want to do is find out how do these things need to be related so that the force on this guy is zero. That means no force is acting on this guy. So that means whatever this guy is pulling with, this guy must also be pulling with, right? That's what that tells me, because if I have a charge here and the net force is zero, they both must be pulling with some force that's going to make the net force on this guy be zero. So how do we actually do that? The net force on Q is zero. How do we mathematically write that down, right? How do we mathematically write that down? Well, let's give it a shot. Let's say the following. Let's write down what we know. The force between Q1 and big Q is given by the following. 1 over 4 pi epsilon naught times Q1 times capital Q over the distance between them squared, r squared. The distance between this guy and this guy is what? You have a here, and you have another a over 2. Right? So if you have problems with fraction math, you have a, this is the distance here, and this is a over 2. So how would you simplify this? This is just a fraction, right? So I can rewrite this as 2a over 2 plus a over 2, because this fraction will reduce to a. I'm just adding these things up to find out what the distance is here, right? So what you have is 3a over 2. In other words, 1 plus a half is 3 halves. So 3 halves a is what the answer is. That's the distance between. So what you're going to have here is 3a over 2, and it's squared because that's the distance between them. Make sure you understand this, because if you don't understand this, nothing that follows will make sense at all. The force between these two guys, the electrostatic force, is simply the charge, this charge times the other charge. The distance between them is 3a over 2. You square it because it's r squared. This stuff, I could have written that big number out, but I'm just going to show you that there are different ways to solve a problem. I'm going to leave it in terms of 1 over 4 pi epsilon naught. I'm not going to do anything with it yet. I'm just going to leave it like that. So this is the force due to this guy. Now, what is the other force? The other force between Q, big Q, and Q2 is going to look much the same. 1 over 4 pi epsilon naught, right? And then I'm going to have Q times Q2. Those are the two charges involved. What's the distance between these guys? The distance between a over 2 and a is just simply a over 2 squared. That's the distance between these guys here. So this is the force because of one, of the charges, and this is the force because of the other charges. Now, because I want this net force to be zero, what I must then do is set them equal to each other. One force has got to balance the other one, right? Because they're basically acting in opposite directions, and so I need to enforce that. So what I'm going to do is I'm going to set them equal to each other. So going from here, 1 over 4 pi epsilon naught times exactly what I've written down here, Q1 times big Q times 3a over 2 squared is going to equal the other guy, 1 over 4 pi epsilon naught times this, which is Q times Q2 over this guy right here, a over 2 squared. Now you can see why I left this problem with this junk out in front and didn't bother worrying about it, because in the end, because you're equating them, they're going to cancel out. That kind of stuff comes with experience. I mean, you wouldn't necessarily see that in the beginning, but you could certainly have put that number in here and that number in here, and you would get exactly the same answer, but in the end, none of it matters because it all cancels. Now also, look further with me. So these are gone now. They divide out. Now, I have a Q on the top here and a Q on the top here, and so I can divide both sides of this equation by capital Q. That means capital Q does not matter at all in the final answer here. Capital Q does not matter at all in the final answer here. Everything else I'm going to have to deal with, so let's go ahead and do that right now. Let's go ahead and continue right here. You have Q1 over. Let's go ahead and start the squaring. 3 squared is 9, a squared over 4. So what I'm going to have over here is the following. Oh, right here I'm going to have Q2 in the numerator. And on the bottom I'm going to do the squaring here, so I'm going to have a squared over, 2 squared is going to give me my 4. Now look at what I have here. I've got quite a few things going on. Let me do one more thing, do our little arrow here. Let's go ahead and simplify this. Let's take this fraction, flip it over and multiply. So I'm going to have 4q1 divided by the 9a squared, right? And on the right hand side I'm going to flip this and multiply, just simplifying here. So I'm going to have 4 times q2 over the a squared that I had on the bottom. Now see what happens here. I have an a squared here and an a squared here, so I can multiply both sides of this by a squared, cancel, just like that. And I have a 4 on the top and a 4 on the top, so I could divide both sides by 4 and get rid of that. So ultimately, all I'm really left with is q sub 1 divided by the number 9 is equal to q sub 2. So just solving a little bit, q sub 1 is going to equal, multiplying by 9, it's going to be the number 9 times q2. Now I know this is a little hard to read because I have q1 is equal to 9q2, but you can put little tails or something on your q's to help you keep them apart if you want. What is this saying? This is saying that whatever charge number 2 is, whatever value it is in coulombs, I multiply it by 9, and that's going to be the value of q sub 1. And if I do that, I'm always going to have a net charge of 0 on that third guy. Now notice that this is sort of independent of whatever charge I choose for q1 and q2. If I pick a positive charge here for q2, then q1 is going to be 9 times bigger, and it's going to be positive. So that makes sense, right? Looking up at the top here, if I choose a positive charge here and a positive charge here, they're both, and since this is positive, they're both going to be pushing because they're both going to be repelling between the two. So if I have positive, positive, it's going to repel. Positive, positive, they're going to repel. They're both going to be pushing on Q, and so that guy's going to have a net force of 0 because Q1, notice, is so much bigger, 9 times bigger than Q2 because it's farther away. Okay? Likewise, if I go down here and I say, well, just for grins, I'm going to put a negative charge for Q2 in. Whatever I end up choosing, then Q1 will be negative and 9 times bigger. So if I go up here, if I put a negative charge in here and a negative charge in here, if I have negative, positive, these are going to attract. So Q is going to be pulled this way. If I have a negative here, I'm going to be trying to pull Q here too because I'll have opposite charges trying to pull it. So in that case, both charges will be attempting to pull on Q. Again, give me a net force of 0. So no matter if you choose positive charges or negative charges, as long as they're the same, which is what this equation is telling you, whatever sign you pick for one charge is going to be carried over into the sign of the other one. And as long as one of them is 9 times bigger than the other one, then you will have a net charge of 0. On that guy. So it's kind of a very common problem that you'll see. You'll be given charges and you'll be asked to say, well, calculate such and such so that the charge on this object will be 0, or the charge on, or the force on this object will be 0, or the force on this object will be nullified or something. And you'll have to set up your equations. You'll have to write the electrostatic forces down due to individual charges, and you'll have to set them equal or do something like that in order to get to the answer. Okay, the next problem is similar, but not quite the same. It says, 2 small spheres have a positive charge, and the combined charge between them is 5 times 10 to the minus 5 coulombs. If each sphere is repelled from the other by a force of 1 Newton, when the spheres are 2 meters apart, what is the charge on each sphere? So here we don't have charges, we don't have electrons, we have spheres. So I told you this Coulomb law thing, that doesn't just apply to atoms, it applies to anything with a charge. An airplane wing can have a charge if you put extra electrons on it. A balloon can have extra electrons if you rub it on your hair. Your feet can have extra electrons if you shuffle on the carpet. Coulomb's law applies to anything with a net charge, any 2 objects with net charge. So here we have 2 small spheres, right? So we have sphere here, and we have a sphere here. And the problem says the combined charge is 5 times 10 to the minus 5. Each sphere is repelled by the other by a force of 1 Newton. So it's 1 Newton repelled, And that basically means that there's a force here of 1 Newton. And there's a force here of 1 Newton, right? When the spheres are 2 meters apart. So this guy is 2 meters from the other guy. What is the charge on each sphere? So this is one of those things you have to start writing down what you know and see where it's going to take you. You know that both charges, this is charge, we're going to call it Q1, and this is charge, we're going to call it Q2. We know from the problem that Q1 plus Q2 is going to equal something, 5 times 10 to the minus 5 coulombs. That's sort of equation number 1, right? The second one is telling us about the force. So I'm going to hang on to this one. That's important. Next, let's work on the Coulomb's law. Coulomb's law is 8.99 times 10 to the 9 times Q1, Q2 over R squared, the force between them. And we're told that the force between them is 1 Newton when the distance between them is 2 meters. 8.99 times 10 to the 9. All right, so what am I trying to do? I'm going to leave Q1 and Q2 here because I don't know what the value of those are, but I do know that the distance between them is 2 meters, so it's 2 squared. Okay, so you see how this is shaping up. I've got one equation that has Q1 and Q2 in it, and I have another equation that also has Q1 and Q2 in it. No other variables. I should be able to solve this system of equations. Right? I should be able to solve the system of equations. So before I do that, let me simplify this a little bit. Let me go ahead and multiply. This is going to be 4 down here. 2 squared is 4, so let me move it over to this side. So I'm going to have 4 is 8.99 times 10 to the 9 times Q1 times Q2. And let me divide both sides by this just to get Q1 and Q2 off by itself. It's going to help me in my solution. So 4 divided by this guy is going to give me 4.45 times 10 to the minus 10. So this is the other equation I want to sort of keep. I've simplified them both. Q1 plus Q2 is equal to something. Q1 times Q2 is equal to something. So what I'm going to do, basically, is I'm going to solve this equation for Q1, and I'm going to plug it in here, and then we're going to go from there. So let's do that right now. Taking this equation down here, Q1 is going to equal 5 times 10 to the minus 5, which is this, minus Q2. Minus Q2. I just solved that equation for Q1, and now I'm going to take it and I'm going to stick it right in here. Whoops, I'm going to actually stick it right there, and I'm going to be able to solve for one of my variables here. Okay, so let me put that in there. Putting this in for Q1, 5 times 10 to the minus 5 minus Q2, that's what I put in the value for here, times Q2 here is equal to 4.45 times 10 to the minus 10. Okay? I just take this guy that I solved for Q1, stick it in there. Now I have an equation in Q2. Let's solve for that. Distributing in the Q2, I'm going to have 5 times 10 to the minus 5 times Q2 minus Q2 times Q2 is Q2 squared is equal to 4.45 times 10 to the minus 10. Okay? Now what I'm going to do is basically move everything over, and I'm going to have a quadratic equation that I'm going to solve. So over here, just rearranging a little bit, I have negative Q2 squared plus 5 times 10 to the minus 5 Q2 minus, because I'm going to subtract this to the other side, 4.45 times 10 to the minus 10 equals 0. Now why did I even do that stuff? Because what I have here is a quadratic equation. I've got something q squared plus something times q2 plus something is equal to 0. And you could use a quadratic formula and go through all of that mess here, but I think you've used a quadratic formula enough in your life to know a is negative 1, b is 5 times 10 to the minus 5, c is negative 4.45 times 10 to the minus 10. So you dump that in your calculator for quadratic formula, or you can solve it by hand, quadratic formula. What you're going to get is Q2 is going to equal 1.2 times 10 to the minus 5 coulombs. 1.2 times 10 to the minus 5 coulombs. That's what Q2 equals. Now, how do you find Q1? You go back up here. You can use either equation, but you can just go back up to this equation for Q1 we solved for. Just take 5 times 10 to the minus 5, subtract what we found here. So Q1 is going to simply equal 5 times 10 to the minus 5 minus what we found right here, 1.2 times 10 to the minus 5. And so Q1, when you do that subtraction, is going to equal 3.8 times 10 to the minus 5 coulombs. So these are the answers here, Q2 and Q1, which is given by this guy right there. Now, also, one more thing I do want to tell you real quick. When you actually solve for a quadratic equation like this, you always get two solutions. So when you solve this in your calculator, one of the solutions was going to be 1.2 times 10 to the minus 5 for Q2. We were able to solve for Q1. Now, the other solution that was given to you was that Q2 was equal to 3.8 times 10 to the minus 5. Exactly what we got over here. And if you were to plug this into this sort of relation here, the corresponding Q1 would have equated 1.2 times 10 to the minus 5. So in other words, no matter what solution you pick, you get the same two numbers. Because look at the symmetry of the problem. You have two spheres. We call one of them Q1, we call one of them Q2. They're 2 meters apart. They're repelling with 1 Newton force. And the sum of the charges is given by this. So whether I say this one has a charge of 1.2 times 10 to the minus 5, and this one has the charge of 3.8 times 10 to the minus 5, I'm going to get the same repulsive force as if I flip the charges around and say this one has a charge of 3.8 times 10 to the minus 5, and this one has the charge of 1.2 times 10 to the minus 5. So, in other words, when you're solving this guy, you get very consistent solutions. The first Q2 that you get is going to be this. Solve for the corresponding Q1. If you pick the other Q2 that pops out of your calculator, you're going to get the other answer over here that's going to allow you to get the other answer over here. Either solution is valid because the problem is symmetrical. It doesn't matter which sphere has which charge because they're both going to satisfy the constraints in the problem. They're both going to cause the same amount of repulsion, and they're both going to add up to the 5 times 10 to the minus 5 that we said they had to end up with. So this is one of those things. You had to write down your one constraint equation, write down Coulomb's law, and then use those systems of equations to find out what the two charges are. And so if you have these two charges here, then you will satisfy the constraints given in that problem. Let's go ahead and erase the board and work a couple of additional problems. Okay, the next problem says two charges, which are 1 microcoulomb and -3 microcoulombs, are 10 centimeters apart. Where can the third charge be located so that no electrostatic force acts on it? Same thing I told you before. A lot of times you'll be given two charges. Where can another one be located where there's no force? So where there's no net force acting on it. So this is just like anything else in physics. You have multiple particles, multiple forces acting because Coulomb's law acts charge for charge. Any pair of charges has those forces between them, so we just need to figure out how to pick the third charge so there's a net force of 0, which means they're going to have to cancel those forces acting on there. Again, mucho important. You have to draw a problem. So what we're going to do here is we're going to label this guy Q1, and we're going to label this guy Q2. And we know that they are 10 centimeters apart, so that's easy enough to do. Now also remember that when you're dealing in these problems, you're dealing with Coulomb's law, you don't want to be working in centimeters. So right away when you see that, just convert it. This is going to equal 0.1 meters. And that's the number we're going to use in our calculations. Okay. Now this charge, Q1, is, let's call it 1 microcoulomb, and Q2 is -3 microcoulomb. So notice right away that they have opposite charges, so they're going to attract each other. If these two particles were left alone, they would just slowly come together and smack into each other. Now the question is, where can the third charge be located in this picture so that there's no electrostatic force? Now let's do some thought experiment here. It's very important in these problems, before you start diving into it, to do a little bit of thinking ahead of time, because a lot of times you can get pretty darn close to the solution without doing any math at all. So let's think about it. I have opposite charges here. They're going to start trying to attract each other, but let's say they don't actually move. I have some rigid post or something and they're held in place. Now I stick another charge between them. let's say I stick a positive charge in here. Let's say I put a, just for giggles here, let's say I stick a positive charge, because the problem doesn't actually state if the third charge is positive or negative. Put a positive charge here. What's going to happen? Well, this is a positive charge, this is a positive charge, so they're going to repel each other. This is a positive, this is a negative, so these are going to attract each other. So this particle is going to move this way, because this guy is going to repel him and this guy is going to attract him. So he's going to begin to move, so there's no way he can have a net force of 0. No matter where you put him, this force is always going to be repulsive and this force is always going to be attractive. Now let's see, what can I do if I put a negative charge in here? A negative charge, how's it going to work? Well, these guys, this is a positive and this is negative, so that's going to attempt to move me this way because they're going to attract each other. And this guy's negative and this guy's negative, so they're going to repel, again, also trying to move him that way. So if I pick a negative charge, this particle is going to move this way. And there's no place I can put a negative charge here that's going to change that. So you cannot put a charge between these two things and have it balance out. The case before was when I had two positive charges or two negative charges. Then it can work because you can have two repulsive forces or two attractive forces holding a charge in place. But when you have different charges, sticking something in the middle is just going to make it move. So let's think about it again. What happens if I put one over here? Let's say I put one over here, and let's say I call this Q3. Right? Let's just say, just for giggles, I have no idea if it's positive or negative, but let's just say it's positive. What's going to happen here? Well, these guys are both positive, so he's going to repel, trying to push the charge this way. And these guys, this is negative and positive, so he's much farther away, but still he's trying to attract him back. And so it looks like these two arrows are in opposite directions, so I may conceivably be able to pick a point here so that this charge will have these forces balance out. The repulsive force from here and the attraction force from there. Perhaps. It's possible. So that's what I'm going to do. I'm going to leave that guy there, and I'm going to say, okay, let's go ahead and go with that and see what happens. So what I'm going to do is I'm going to say the distance here, I'm going to call it D, because that's ultimately what I'm trying to do. The problem says, where must a charge be located? So I'm going to go ahead and put, this is the distance D, and I'm going to try to solve for D. Right? And we're going to go from there. So the constraint is that the force is 0 on Q3. That's the major constraint here. So the Coulomb law is 8.99 times 10 to the 9. Q1, Q2, R squared. Q1, Q2, R squared, right, in general. Now, in my particular problem, I need to balance these guys. So basically what I'm going to do is I'm going to say the force Q1, between Q1 and Q3, this guy right here, plus the force between Q3 and Q2, the force between these guys, I'm going to basically say those guys have to be 0. They have to basically subtract out or cancel out or whatever. And remember, we said one of them was pointing this way and the other one's trying to pull back, so it should be possible. So let's go ahead and plug in what we know for Coulomb's law and do it. What we have here is Coulomb's law is going to be 8.99 times 10 to the 9. So what I'm going to actually do is plug in the values that I know and see how far we can get to our solution. So Q1, which is one of the charges here, is 1 times 10 to the negative 6 coulombs, right? And Q3, I don't know what that is, so I'm going to put it there as Q sub 3. Okay? And the distance between these two charges I've labeled in my diagram as D, so I'm going to put D squared. Right? Make sure you understand this. This is just Coulomb's law. Constant, charge, this charge times this charge divided by the distance squared between them. That's the force between them. Now over here I have the other Coulomb law that I'm going to write down right here as 8.99 times 10 to the 9 times. And I have this charge and this charge. So let's go ahead and write that down. I'm going to have 3 times 10 to the minus 6 coulombs times Q3 over the distance between these guys. Now notice if this is the distance D that I've labeled, then this distance right here has got to be D plus 0.1. Because this is 0.1, this is D, so this is D plus 0.1. So you have to write down what you reflected in your diagram. And this is a great example of why you have to draw a diagram. If you didn't draw this diagram, you would never get the right stuff in here. You'd probably screw it up. All right, so what we've got here is we have the two Coulomb forces, and we want to make sure that they cancel. Now remember, one of them in our little picture here we said was pointing in one direction, and the other one was pointing in the other direction. So let's say we have this one, and we're going to basically subtract off the other force, and we're going to say it's 0. Right? We're going to say it's 0. Now I did that because notice that in this equation, really it's a negative charge here. I could have stuck a negative in here, and I could have had this force plus this force is 0. But again, trying to stay consistent, if I just put positive values everywhere and realize what's happening, if you say that this is a positive charge, let's say, then this force is going to be trying to push it away, right? And then this force over here is going to be trying to pull it back. So if I take this force and I subtract off the force coming from this one, then I should be able to say that the subtraction of these guys should give me 0. Take this force, subtract off the force in the other direction, and hopefully I'll get 0 at the end result. So now it's just a matter of working through it. And you've got this constant, which is going to cancel with this one. Doesn't matter at all. And also, think about this for a second. I can take this and move it to the other side of the equal sign. So this Q3 is really going to cancel with this Q3 as well. In other words, the final answer has nothing to do with Q3. It could be positive, could be negative, could be 5 coulombs or 10 coulombs. It doesn't really matter because the end result is, since this charge is acted upon by both of the other charges, the value of this isn't really relevant because the attraction and repulsion is going to be canceled in either case. All right. So what we're going to do now is just go ahead and rewrite things to make it clear. We're going to have 1 times 10 to the minus 6 over d squared. And I'm going to take this and move it to the other side of the equation over here. So I'm going to have 3 times 10 to the minus 6 over here. And I'm going to have d plus 0.1 over there. And this is going to be squared. I forgot to square that. This is going to be squared right here. Right? D squared, d squared. Okay, now it just comes down to algebra. You just at this point have to really roll your sleeves up and get going with this. So the first thing I'm going to do is take this denominator and move it over here by multiplying both sides by that guy. So I'm going to have 1 times 10 to the minus 6 times d plus 0.1 squared over d squared is equal to, and on the right you're going to have this, 3 times 10 to the minus 6th. The only reason I really did that is because I really want d to be on one side of the equation, because ultimately that's what I'm trying to solve for. Okay. Now what I can do at this point is I can take, this is just a number, I can divide both sides by this, so I'll have 3 times 10 to the minus 6 divided by this, and so what I'm going to have on the left is d plus 0.1 squared over d squared is equal to, take this, divide by this, and you're just going to get a nice number 3. A nice number 3. So what I want to do is take this all the way back up over here and continue. I had written down over there d plus 0.1 squared over d squared is equal to 3. Now I'm just solving for d at this point. How do you go about this? Well, you need to do FOIL here. There's no way around that, so let's just go ahead and do that. On this side of the equation, I'm going to have d squared plus 2 times 2ab, so it's 2 times d times 0.1, so you're going to have 0.2d, so d squared plus 2 times this plus 0.1 squared is going to give you 0.01 is going to equal, and I'm going to go ahead and just take this and move it over here to help me out. I'm going to multiply both sides by d squared, so 3d squared. So I have a quadratic. I'm going to move this guy back over here, and I'm going to get negative 2d squared plus 0.2d plus 0.01 is equal to 0. Negative 2d squared plus 0.2d plus 0.01 is equal to 0. And this is just a quadratic, just like you could take and plug into the quadratic formula or into your calculator. And what you will get is d is going to be equal to 0.136 meters, which is, if you move the decimal place, 13.6 centimeters. The other value for D that you get when you plug into this guy is a negative number, negative 0.036. But it's not valid because we define D to be over here. If D is negative, that means it's really in the middle, and we already said that that cannot satisfy this because if you put it in the middle, the net charge on that guy is not going to be 0. It's impossible. We already talked about that. So the right value to pick is the 13.6 centimeters. So the answer to the problem is the charge must be located 13.6 centimeters left of the 1 microcoulomb charge. And it kind of makes sense when you think about it because it has to be over here because this charge is smaller than this one. So if you put a charge here, this guy's going to be repelling him, let's just say, and this guy's going to be attracting him. And it has to be over here because this is a bigger charge. He's pulling, in other words, he's farther away, but he's a bigger charge. So because he's bigger and farther away, he can cancel the charge that's actually sitting closer. Starting from the top, you want to have a 0 force on this guy here. So what you have to do is look at Coulomb's law and write an equation equating the forces. This is an equation between these two charges right here. Constant, charge 1, charge 2, distance between them, squared. This is an equation between this force, this charge, and this charge right here. Constant, charge number 1, charge number 2, distance between them, squared, right? The entire distance between them, squared. And at this point, you just have to make sure that you're getting your signs right. So you have one force minus the other force equals 0, right? Cancel out the constant, that doesn't matter. Q doesn't matter either because you could divide both sides by Q3 and they would just all disappear. And at that point, it just becomes algebra. You move this guy to the right-hand side of the equal sign. You move these D's up over here in the numerator. You start taking the constant and doing the division to get the constant squared away. And then when you move over here, then go ahead and take your D over here, do FOIL to get this, move your 3D squared back, collect terms, and then you finally end up with a polynomial that you know how to solve. So you're trying to solve for D. You get two answers for D. One of them doesn't make sense because this one puts the charge back in the middle, which we said can't happen. So, lengthy problem. Good problem, though. Good test problem. You're very, very likely to get something like this on one of your tests. Let's go ahead and erase the board and work one more. Okay, the final problem says a charge capital Q is fixed at each of two opposite corners of a square. If a charge little q is placed at the other two corners, if the net electrostatic force on each big capital Q is 0, what is capital Q in terms of little q? So this is exactly the same kind of problem we saw before. It's just a little bit more complicated because the charges are not in a single straight line. And so we have to start thinking in terms of our vectors. So we have a square. All right, so let me draw a little square. Actually, let me draw a square and make it a little bit smaller like this. So we have two charges at opposite corners. We call them capital Q. And we have two other charges at the other corners. We call them little q. The distance between them, right, this is a square, it says. The distance is d, so the distance here is also d. And the distance here is d, and the distance here is d because it's a square, right? So I'll just go ahead and do that. And this is stuff that you would extract just by reading the problem. So the question is, okay, so if we put these guys at the other corners, if the net electrostatic force on each of these guys is 0, what is big Q in terms of little q? So the kind of the constraint, so to speak, is that each of these guys have an electrostatic force of 0. So we really need to start thinking about what this guy's really doing and what the actual forces would actually look like. So think about it. This Q, let's just look at one of these for a second. This Q right here, this big Q, what would be the forces acting on it? Well, there would be a Coulomb force coming from this charge here, because of these charges. There would be a Coulomb force coming from these two charges, trying to move this guy, and there would be another Coulomb force from the other Q down at the other corner. It's a little farther away, but he's going to be trying to push him too. So just for the sake of wrapping it around your head, pretend all of these are positive because we don't know what the signs are, so pretend they're all positive. What would this situation then look like? All right? What it would look like is, if this is positive and this is positive, which way would this be trying to push? He would be trying to push up, right? Because it would be a repulsive force. So he'd be trying to push up. And what would this force be due to this charge? Well, if these are two positive charges, he's going to be pushing it this way because, again, it's repulsive. He's trying to push him away. All right? So I have those two guys. So I have one that's vertical and one that's horizontal. So what I want to do is sort of write that down for a second. this guy right here, right? Just think about this. The force here, I'm not going to write all of the constants, but Coulomb's law in general is a giant constant times Q times big Q over r squared, which is the distance d. We'll get to that in just a second. Okay? And then this guy right here, this is what we're going to call it, let's say the vertical force. The vertical force there. And then this guy is going to look exactly the same. The force on this guy is C, some constant. C, we already know what it is. It's the constant we've been using all along. And it's going to be Q times Q over R squared. So it's the same exact magnitude of forces coming from these guys. It's just one is going horizontal and one is going vertical. So you have a vector situation here, just like in projectile motion. You know, you're throwing something and the velocity is kind of going at an angle. Well, we know how to decompose that into horizontal motion and vertical motion. You have to think the same way in terms of any vector, and this is just a vector here. It's a force. So when you have two guys going this way and this way, and they're trying to push this guy like this. This guy is going to try to push it up, and this guy is going to try to push it over. But the resultant of those two forces from these two particles trying to act on this, what is it going to do? This is going to try to, this is Q, let me just do it like this. It's going to attempt to try to push this guy this way. From these two guys here, he's going to attempt to be the resultant force is going to push it that way. And notice that we have another charge down here. So this guy is going to have some sort of force acting along exactly the same line, and he's going to be trying to push or pull like this depending on the sign of him. So that's how it's going to balance. That's the only way it's going to work, is you've got these two charges, one pushing up, one pushing over. The charge down here is going to be trying to push or pull to try to balance the resultant force there. And that's what you have to think of in terms of vectors. If you don't decompose it in terms of vectors and realize that there's going to be a resultant force here, then there's not going to be any way that you can continue. All right, so let's go ahead and find out what this resultant force is right here. Right? Let's do that right now. The diagonal force right here is going to equal to the following: the square root of the two forces acting. Because look, this is a triangle. You've got a hypotenuse right here, and you've got your two sides here. So this is just simply a right triangle. So what you're going to have is, you're going to have constant times Q over, and instead of R, I'm going to go ahead and put D in now, D squared, okay, this quantity squared, plus constant times Q over D squared, and this guy squared. Make sure you understand what I'm doing here before I go on. What I'm trying to do is I'm saying, okay, these two forces, one's acting horizontal, one's acting vertical. I'm trying to find the resultant. The way you find the resultant is you'll use the Pythagorean theorem. It's the square root of the squares of both sides of this vector, just like a triangle, right? Now, each leg, I've already told you what they were, the horizontal and the vertical side, so I'm just plugging it in there. Coulomb constant times the two charges in question divided by the distance between them, d squared, right? And then the same exact thing here. One's going up, one's going over. The reason that they're squared on the outside is because I'm trying to find the resultant coming up right at the middle there. So, what are you left with here? This guy is going to equal square root of, let's go, these are exactly the same things in here in the middle, so I'm going to have 2 times C Q over D squared. These are just added together, so I'm just going to stick a 2 there because it's this plus this. So you're going to have 2 times this quantity right here. And this is going to reduce down to the following. This is a square and a square root, so I'm going to reduce it to the square root of 2 times a constant times Q over D squared. All I did here is I take the square root here. Square root of 2 is 2, that can come out. Square root of this quantity just drops the outside square here, so I'm left with this junk right in the middle. So this is the resultant. This is the resultant. So it's sort of an intermediate answer that's very, very important. So I'm going to kind of circle it here. Now in our drawing, let's pretend this guy is coming up here. Now, if I want to balance this resultant with some electrostatic force from a charge down here, how would I do that? I would say that the force that I got here had to be equal and opposite to the force that's exerted by the other Q down here. In other words, taking this guy, the square root of 2 times constant times Q d squared, that's the force going that way, plus the force exerted by the other Q down here. I haven't even done that one yet. That's an electrostatic force between these two guys has got to be equal 0. What would that would be? It'd be a constant times Q, because both Q's are exactly the same in that case, divided by the distance between them. So let me ask you this. What is the distance between these two guys here? Again, it's Pythagorean theorem, right? It's the square root of d squared plus d squared, which is the square root of 2d squared, which is square root of 2 times d. That is the distance here, square root of 2 times d. So it's just a little bit of geometry there, square root of 2 times d. So I'll put square root of 2 times d, that's the distance. I have to square it because it's distance squared. So the two forces, this is the resultant of the other two, plus whatever the third one is, has got to be equal to 0, because that's what I'm trying to say. The force on each Q is 0. So what can I do? Can I simplify anything? Well, notice right away that this constant C and this constant C is going to disappear. A lot of times you're going to find that happens. That's why I abbreviated it with a C instead of carrying through all the little letters for everything. One of these Q's is going to cancel with one of these Q's here, because I could divide both sides by Q, right? So that gets me in pretty good shape. So let's continue on going. We have the square root of 2, and over here I'm going to have Q over d squared plus, and over here I'm going to have Q over, now let's square the bottom. Square root of 2 squared is going to give me a 2. And d squared is going to give me a d squared, and that's equal to 0. Now further, notice that this d squared can cancel with this d squared, because I can multiply this entire equation by d squared and get rid of both of them, right? So let's go ahead and move this over to the right-hand side. So I'll have square root of 2 times q is equal to negative q over 2. Just moving that over there. And just doing a little bit more manipulation. Let's go ahead and solve for big Q. So big Q is going to equal negative 2 times the square root of 2 times little q. Just multiplying by 2 here, taking care of the negative right there, and that's the answer. So big Q must be equal to whatever this number is, 2 times the square root of 2 times whatever little q is, but it has to be opposite signs. Now think about that for a second and make sure that makes sense to you. It has to be opposite signs because the way I've drawn it, if I had positive charges for everything, yes, these would be up, but this would be a repulsive force as well if they were all positive, and so these would be trying to push it apart too, and I would not have a net zero force. So you kind of make some assumptions in your drawing, solve the problem, and then whatever you get at the end is going to tell you what truth really is. The charges must be opposite, and the magnitudes of the charges is given by this guy right here. So what it's basically saying is, let's say I pick a positive for Q. So let's go ahead and do that right now. Let's say this is a positive for Q, and let's say this is a positive for Q. Then that would mean that big Q has got to be negative, and it's got to be larger too. So this would be negative charge, and this over here would be a negative charge. Now let's see, is this possible to balance here? So in that case, I'm going to have a little bit different kind of free body diagram here, because if this is positive and negative, I'm going to have an attractive force. Let's go ahead and clean up my drawing and just get rid of this for a second. That means that this force is going to be, I really would like to use a different color here. This force would be attractive like this, because these two are attractive. And then this force coming down is also going to be attractive, because this is a negative and positive, so that's attractive. So the resultant force of the two coming right on down the line is going to be down this direction. That's going to be the resultant. So if this is the resultant of these forces coming here, but if these guys are both negative, then they're going to attempt to repel each other, right? Which means I'm going to have a chance at fighting back this force, so the net force is going to be 0 here. So the answer you get from your problem, you should always see if it makes sense. The charges should be opposite in the end. It does make sense, because if they're opposite the way I've drawn it, you got force here, resultant force from the two. If these are negative, I'm going to have a repulsive force trying to fight it, and then I'll be able to cancel the force. So What we did is we drew it one way, we wrote the Coulomb force down, we said, okay, what is going to be the resultant here? You have 1 Coulomb force from one plus 1 Coulomb force of another. We're taking the resultant, so we take it just like Pythagorean theorem, square root of the square of both, combine like terms in the middle, take the square root, and we get this. Now we take this resultant and we add it to whatever the force must be coming from the other Q, and the result of that must be 0. And so then after that we're just doing algebra to find that the big Q has got to be equal to negative 2 times the square root of 2 times little q. This was a very lengthy section and a very necessary section because everything builds on the Coulomb's law, right? Later on we're going to get to electric fields and electric potentials and circuits, and all that stuff is really going to boil down to what is an electric charge and the fact that when you have two charges, they repel or they attract. So my name is Jason. I hope you've gotten a lot out of this section. Keep on going down through the line into these sections that follow, one step at a time, and you'll be very well versed in electricity and magnetism.